Thank you for being here. So yes, as Martina said, I'll say things about that topic, which is very long to repeat, so I won't. The main idea is that there are three notions of computational strength for reals that we did not know whether they would be separate or the same. And I will show you now that they are separate. And this is recent joint work with Noam Greenberg. So first, I'll tell you how to extract notions of computational strength from cardinal characteristics. And then I'll state precisely what the problem is and what the result is. So let's start from cardinal characteristics. So cardinal characteristics of a continuum are basically cardinals which are related to some combinatorial problems. And yeah, so they come from problems in the sense that they are the minimal size of a complete solution set for a certain problem. So I'll give you an example of that. So let's say that our problem is the domination problem. So we are given an instance which is a function in their space, and the solution for f is some g in the Baire space which dominates. Oh, my g's and f's looks the same. Oh, no, okay. G dominates f. Okay, so the dominating number is the minimal size of some set A, such that for every instance of the domination problem, call it x, there is a y in A which solves that problem for the instance x. And yeah, many cardinal characteristics are of this form. All of the cardinal characteristics in the Sikon diagram are of this form. Okay, so this is the setting. And what is a typical proof? So if A and B are cardinal characteristics, and we denote PA and PB the problems that these cardinal characteristics come from. A typical proof of ZFC implies that that A is not bigger than B goes through showing that PA is simpler than PB, sorry, where simpler means that it's an easier problem to solve in some sense. Okay, what would the set theories say that simpler means? The set theories would say that there exist two functions, phi instance and phi solution, such that for all x instance of PA, phi instance of x is instance of PB, and for all y solving phi instance x, phi solution of y solves x. Where, when I say that something solves something else, of course, it's related to the problem that makes sense in the context. This has many names. One that I've heard first was Taki connection. And why is this enough to show that A is not larger than B? Because if this is the case and S is a complete solution set, for for PB, yes, then phi solution of S is a complete solution set for PA. Why is this? Well, because you take some X instance of PA, send it with phi instance to some instance of PB that is called phi instance of X. And then you can always find some Y in S, which solves this phi inst X. And by the definition of the Taki connection, phi solution of Y solves X. So we started from any instance of PA, and we got to some solution which belongs to this set here. Okay, so this is the way that these things are shown. Yeah, so starting to my knowledge in 2010 with a PhD student of Ruprecht, people started to notice that the Taki connections of the set theorist, in most cases, certainly in all cases in cardinal characteristics in Sikon diagram, are actually effective. And we don't need to go into details to what kind of effectivity we're talking about. It's in a paper of Noam, Dan, and Kuiper. They call it effective morphism, and it's really close to a strong bioreproducibility. It's not quite, but it's basically the same thing. And what we actually need, all we need, is to have that the effectivity, let's say, is that for all x, both phi instance of x is irreducible to x, and also phi solution of x is of course, these are two different x's because they belong to different domains, but you get what I mean. So in most cases, and certainly all the cases that we're worried about, these morphisms are effective in this sense. Okay, so now we introduce notions of computational strength related to cardinal characteristics. So let's say computational strength. So if P is a problem, I guess normally problems have both solutions and answers in the Baire space, both instances and solutions in the Baire space. Sometimes the Baire space will be taken as a set of codes, but that is all standard stuff. If P is a problem, we see one kind of notion of computational strength, which is the following. We say that X is in H of P, which stands for high of P, if X computes some Y such that for all Z computable instances of P, Y solves Z. And you might be wondering, why does such a Y have to exist? and this is because when our problems come from cardinal characteristics are uncountable. So if you have a countable family of instances, you must have a solution that solves them all at once. This made more sense earlier. Okay, so this is one of the notions of computational strength. One that might be more natural is the non-lowness class for P. X belongs in the non-lowness class for P if it computes a Y such that no computable Z solves Y. And it turns out that these are connected by duality, so every problem has a dual, P dual, and this is defined as, if you see problems as relations, then P dual, like X, P dual Y, is defined as Y does not P X. Where here I'm writing X P Y to mean Y solves. So with this kind of duality, you can see that the highness class for the dual problem is equal to the non-lowness class for the original problem. And of course, duality is like P dual dual is equal to P. So you can switch duals here. Like you can write another dual, like you can erase the dual here and write it here. So these are the sort of notions of computational strength that come from problems related to cardinal characteristics. And one way to, oh, there it is. Oh no, I should do this. Yes, so this type of notion can be relativized to any countable idea. So if I is a Turing idea, and I is countable, you say that X is in non-lowness I of P if X computes with the help of some Z in I, some Y such that Y has no solutions in I. So in the following, I will abbreviate this. Oh wait, abbreviate this by saying that Y is I irreducible to X. So saying that there is some Z in I such that Y is Turing reducible to X plus Z will be abbreviated to X is irreducible to Y. bear with me because we're almost done with the boring stuff. So this is the relativization to countable ideals. And why do we care about these computational strength notions, and why can we see them as sort of effective analogs of cardinal characteristics? This is because it is not so hard to see that if you have an effective morphism between PA and PB, I will write effective morphism like this. It's an overloaded symbol, but I will not be using it so much. If we have this effective morphism, then you can see H of P B as good solutions for PB, like strong solutions for PB. And if you have an effective morphism, then a strong solution for PB is also a strong solution for PA. Yeah, as I said, this can be seen only by assuming this much effectivity. Why is that? Well, say that so X in here solves all computable instances of PB. So if I'm given Y computable instance of PA, then phi inst of Y computable. Therefore, X solves it. Of phi inst of Y, and therefore phi sol of X solves Y. So phi sol of phi sol of X solves Y, which means that phi sol of X is Turing reducible to X and solves all computable PA instances. And here you can actually replace computable with in I, and here again it will be in I, and here would be I reducible. So this means that if you have an effective morphism, then for any countable ideal, you also have this inclusion, where H superscript I PB stands for the relativization of the highness class. So this will be for every I. So we have one half of the story here. We know that in all cases, most cases, probably all cases, certainly all cases in this Sikon diagram, ZFC provable inequalities are witnessed by some morphisms, and these are effective. So this means that if you have a ZFC provable inequality, then you have a containment of highness classes. And this is the case for relativized to any countable Turing ideal. Okay, so let's go to the other side. Okay, so now let's see that the converse is also true. So in case we in case we want to prove that inequality between cardinal characteristics is consistently strict, so we want to prove that that A is less than B. What the set theories typically does is they take some model of ZFC and they force over some model V to add a hard instance for the problem B, so something that is in NLV of B. Got some X that is in here, but it's not a hard instance for the problem A. The effect of this is that what was previously a complete solution set for B is no longer a complete solution set, but what was previously a complete solution set for A is still a complete solution set. Then the set theorist needs to worry about iterations, so plus some iteration in which everything goes well, hopefully. Okay, so this is basically the outline of such a proof. And also in our context, since we have that this is always true if there is an effective morphism, then if we have that these, like the difference between these classes is non-empty, then this is kind of like any element that is in this difference is a witness to the non-existence of a morphism. Because if the morphism existed, then we would have this. Or here maybe I should have forgot to say that I showed you that the inclusion of the highness classes holds with reversing A and B. If you take the non-lowness classes, then A and B go back to their places. Yeah. So what we do have is that if you consider the cardinal characteristics in the Zichron diagram, then the diagram of inclusion, the diagram of inequalities, and so ZFC provable inequalities and all the separations that are consistent is exactly reflected in the diagram of inclusions of the non-lowness classes. So in other words, if V is a countable model of ZFC, and A and B are cardinal characteristics, then non-lowness, say, classical cardinal characteristic in Zichron diagram. Then non-lowness of A is included in non-lowness of B if and only if ZFC proves A is less than or equal to B. So this means that by looking at these classes, we can see all within a model without doing like forcing or going outside of our model, without looking at consistency statements. We have sort of a trace of which problems are harder than others. And this makes sense in the presence of the continuum hypothesis, for example. So yeah, this is the reason why this work is interesting. And so far, I've basically told you preliminaries, and this is all contained in a paper of Noam, Dan, and Kuiper. So what I want to tell you about today is separation of some of these classes that are supposed to be separate in the sense that they are separate when relativized to any countable model of ZSE, but collapse in the computable world. So what do I mean by that? Now it's time to erase stuff. Much? Okay. So what I mean by that is that there are three classes. These classes are related. One is related to the problem of domination. So let's say NL of this problem. Well, no, this is actually the escaping problem, so it should be this. A hard instance for the escaping problem is a dominating function. So this is dominating, which in the computable case is I, by Martin's theorem. And then there are other problems which are related to the cofinalities of the null ideal and the meager ideal. So I'll just write one of them, the other is the same, with m replaced with n. So the spill problem is the following. I give you an instance, which is some m sigma 0 to meager. And the solution would be some n, which is sigma 0 to meager. And n is not contained. No, actually, now that I think about it, it's not cofinalities, it's additivity, but the cardinal in question doesn't really matter at this point. And with the null ideal is the same, but here you replace it with, to be precise, Schnorr null sets, but for the purpose of this talk, just null set is okay. So then we have spill of n. And the non-lowness class for this is called strongly meager engulfing, which I will abbreviate as SME. And this means, so X is in here. If it computes a meager set, which is a superset of all computable sigma 2 meager sets. And for the null case, it's SNE, and X is in SNE if it computes a null set, which is a superset of all computable null sets. So these three classes here, unrelativized, they all coincide. Why is that the case? That is the case because there is another class which does not have a correspondence in the set theory world, which is listing, and listing would be, so X is in listing if there is a Y Turing reducible to X, such that for all computable Z in the bare space, there is an n such that the nth column of Y is equal to Z. And it's not too difficult to see, but I won't show it because I don't have time, that in the computable world, listing coincides with I. And the inclusions given by provable ZFC inequalities tell you that SNE is a subset of SME, which is a subset of dominating. And again, something else that is not too hard to see is that listing is a subset of SNE. And this holds relativized to any ideal. In the computable case, when this and this coincide, then they all collapse. So I might be getting closer to actually saying what I need to say. What? Ah, yeah, makes sense. Thank you. Yeah. Thank you. So I'm almost getting to the point where I can state the result. Thank you. So emulating the set theory proof for the separation of these classes requires, here it requires labor forcing, and here it requires a two-step iteration of Cohen forcing and Heckler forcing. And these proofs can be carried out in ATR naught with exactly these forcings. So this means, yes, yeah. So Heckler forcing is given by pairs tau and f. Tau is a finite string, so natural number, and f is in the Baire space. And tau1 f1 extends tau0 f0 if tau1 extends, like is a tau0 is a prefix of tau1, and let's say above the length of tau0, tau1 majorizes f0. So you need to extend this string. Sorry, f1 is everywhere larger than f0. So basically, you need to extend this by going to the right of f at every point, and then you need to find yourself a larger bound. Yeah, so these forcings show the separation of these classes in set theory, and their proofs go through in ATR naught. This means that if I is a model of ATR naught, then ISNE is not the same as ISNE, which is not the same as I dominating. On the other hand, this collapse, this collapse here, holds not only for the computable ideal, but also for, let's say, this holds, in some sense, no matter how many jumps you have in your ideal, no matter how many jumps within a computable ordinal, you will still have this sort of collapse. So if you say that I beta is the set of x which is computable in 0 alpha, alpha less than beta, and say beta is limit, then this collapse will happen again. So no matter how large of a computable number of jumps you want to have in your ideal, you're not going to be able to prove the separation at all because the separation doesn't exist. Moreover, Dan one day told us of an argument that shows that if a real x is even a bit generic, let's just leave it at this, for either Lever or Heckler forcing, then x is Heckler forcing restricted to delta 1, then x is delta 1 listing. So recapitulating, if I is a model of ATR naught, then we're fine. We have the separation. We know how to get them. If I is a model of less, well, in some sense, less than delta 1 comprehension, then the separations are not there, not even there. And so our goal would be to show that the separations are there over delta 1 comprehension. And that is, in fact, our theorem that I will now write. And we have this hint from Dan that Heckler forcing and Lever forcing are not going to work to show the separation, because what you get, like Lever and Heckler forcing are candidates to get stuff that is in here and either not in here or not in here, and definitely not in here. So it's not going to work like that. So when do I need to stop? Okay. So now we can finally state the result. Theorem would be Greenberg and me, which is if I is a model of delta 1 comprehension, then I, S, and E, I dominating differ. They are pairwise not the same class. Yeah, so now I should mention actually that this is not the only instance of a collapse of non-lowness classes. In the computable world, there is one more, and this other collapse is solved as soon as you move to an ideal that is a model of the DNR principle, so much, much lower. So in some sense, you can say that in delta 1 comprehension, everything works. Like the inclusions that are supposed to be there are there because they're there for any ideal. And the non-inclusions that are present in the set theoretic setting are also present here. So if you believe that the inclusion diagram of non-lowness classes should be the effective correspondent of the Zwickau diagram, then in delta 1 comprehension, the effective Zwickau diagram is fine. Everything is at its place. So now I'll tell you the main ideas behind these proofs. These proofs are not so different from the original ones, if I have to be honest, in the sense that we're still trying to add, well, obviously we're trying to add dominating real that is not strongly mirror engulfing and a strongly mirror engulfing real that is not strongly null engulfing. And basically we're still using a modification of Lever forcing here and a modification of Heckler forcing here. It's just that we need to come up with some modifications that work well with delta 1 comprehension, because we know that the original ones don't. So the starting point would be Bushy tree forcing. And so in the classical finitary setting, Bushy tree forcing would be something that uses computable trees that are bushy in the sense that every node splits a good bunch, like has a good bunch of children, which, I mean, can mean several things depending on the context. In the most basic context, you're asking for, say, every node has at least 10 children, and that's what makes a tree bushy. And the typical technique of bushy tree forcing is that a condition is not only made by such a tree, but also by a bad set, like a bad set of strings. So you have a T bushy tree and a bad set of strings B. And B is a set that is sort of the code for an open set of bare space that you're trying to avoid. So you want to have that T and B force that your generic is, so let's call the generic FG. FG is in the branches of T, but is not in the open set that is generated by B. So the open set of the elements of bare space which have an element of B as a prefix. And why does this why is this framework used? It is used because normally T is computable, whereas B is CE. And the fact that B is CE sort of relieves you of the burden of having to calculate B. Like, you don't need to have a computable description of B. You can use more complicated sets than just computable. But the fact that it's CE allows you to refine conditions dynamically, in some sense. So this was our starting point, and this is what we're going to do to have an analog of Lever forcing that works well with delta 1 sets. So let me. Okay, it's fine. Okay, so that's sort of the idea. Maybe I can take some seconds to tell you about the high-level way of building the Lever forcing. So a Lever tree is a tree where each node has infinitely many splits, and you have no leaves. What we work with, our modification would be like omega bushy trees with bad sets. So an omega bushy tree is still a tree that has, in which every node has an infinite amount of splitting. But it now we're allowing leaves in our trees. And we're allowing leaves, but the leaves are included in the bad set, and the bad set needs to be small, comparatively small. So the recipe essentially was finding a smallness notion that made sense. And, well, we found a smallness notion, or rather a bigness notion, that made sense in the sense that, well, a set is big. Well, a union of two sets is big if and only if at least one of the two is big, and then you can sort of concatenate to have that. If B hat stands for the set of strings above which B is big, then we have that B hat is equal to B hat. So we're sort of, this hat operation is a sort of a closure operator on a set of strings. And the last thing is that B hat is pi11 of B. So if we force with Bushy trees that are hyperarithmetic and bad sets are pi11, then we sort of recover the same kind of setting of those Bushy trees. And well, you can then prove the properties of Lever forcing that you're interested in without having the burden of calculating these bad sets, which is possible in ATR naught, but it's not possible in delta 1 comprehension. And once you recover those properties, you can go through with the original proof to obtain the separation that you're after. And one last thing is that this same smallness / bigness notion can be used to obtain a modification of Heckler forcing. Well, you use the same smallness notion to obtain a modification of Heckler forcing that also works. And that's the outline of the proof of the theorem. And yeah, so that is all.